All right, so here they're saying which of the following pairs have identical shapes, right? And this is clearly a question from the chapter chemical bonding. So by now I know that you must be very comfortable with the chapter, so I'm not going to spend a lot of time solving this question. We are going to solve it completely, yes, but we're going to run through it very quickly, and I'm going to assume that you know a lot of things and that you're able to solve it with me. Okay, so let's get started. First we have option A, CF4 and SF4. So let's see, I have option A, CF4, comma, SF4. I have to find out whether they have identical shape. So first we have CF4, where carbon is the central atom. It has 4 electrons available for bonding and there are 4 fluorine atoms. So this is what it's going to look like. Okay, this is the basic Lewis dot structure that I have drawn. So it has 4 electrons available for bonding and all 4 of them are gone in forming bond pairs with fluorine. So from here I can say the steric number is equal to 4. Okay, if the steric number is 4, then the hybridization that we expect is sp3 and the shape that we expect is tetrahedral. Okay, we expect a tetrahedral shape, and since there are no lone pairs, then yes, CF4 will show a tetrahedral shape. Then let's talk about SF4. So in the case of SF4, you have sulfur as the central atom, which has 6 electrons in its outermost shell, in its valence shell, because sulfur is a group 16 element. Okay, so it has 6 electrons available for bonding and it has 4 fluorines to form bonds with. So this is what it's going to look like. It has this 1 electron here and 1 electron, on the top. So this is what it's going to look like. Okay, these are like, there's 1 more fluorine here and 1 more fluorine here. It's not like a double bond with the fluorine. Okay, so here what can you see? You can see the steric number is 4 bond pairs plus 1 lone pair. Steric number is 5. So this is going to be sp3 dehybridization. sp3 dehybridization, the geometry that is expected is going to be a trigonal bipyramidal, but here since you have a lone pair, it's not going to be trigonal bipyramidal anymore. Instead, what you will observe is a seesaw shape. Okay, so seesaw shape, not a 2D structure but a 3D structure indeed. So yeah, CF4 has a tetrahedral shape, SF4 has a seesaw shape, so definitely their shapes are not identical. I'll write it here. This is tetrahedral, this is seesaw. Then we have option B, XCF2 and CO2. So let's dive into that. Option B, we have XCF2 and CO2. So let's start with XCF2, where xenon is my central atom and I have 1, 2, 3, 4, 5, 6, 7 and 8. 8 electrons available for bonding. Xenon is a group 18 element. It's a noble gas. It's bonding with fluorine. So 1 bond here and 1 bond here. You can see the steric number, 2 bond pairs plus 3 lone pairs is 5. sp3 dehybridization. You would expect a trigonal bipyramidal shape, but because you have only 2 bond pairs and 3 lone pairs, the shape it is going to take is going to be linear. Okay, now come down to carbon dioxide. So in case of carbon dioxide, what happens is carbon is the central atom which has 4 electrons available for bonding. So it forms a double bond with oxygen like this and like this. So 2 oxygens which are present, which are there to form bonds, both of them form double bonds with the carbon, because of which now here the steric number is going to be 2. This is going to be sp hybridized, and due to sp hybridization it is going to be linear in shape. Okay, so great, we found the pair that's actually going to be the answer to this question, but we are going to solve for the rest of it. We're not the sort of players that leave mid-match, right? Let's complete everything. So we have option C. You have BF3 and you have PCl3. Okay, so let's start with BF3, where boron is going to be your central atom. So in case of BF3, you have boron as a central atom which has 1, 2 and 3 electrons available for bonding, and all 3 of them are taken by 1 fluorine atom for bonding, which means here your steric number is equal to 3. Your hybridization is going to be sp2, and in case of sp2 hybridization, the shape that we observe is trigonal planar. Great. Now let's talk about PCl3. So in case of PCl3, you have phosphorus as the central atom without a shadow of a doubt, and you have 5 electrons available for bonding because phosphorus is a group 15 element. Okay, now here you have 3 of them gone in forming bonds with chlorine, and you have 1 lone pair. So steric number is 3 plus 1, which is equal to 4. So it is going to be sp3 hybridized, and you would expect the geometry that you would expect is tetrahedral, but due to the presence of the lone pair, the shape that we see is pyramidal. Okay, so this is going to be trigonal, but I'm just writing triangular, right? And this is going to be pyramidal. Cool, sorted. We have one last option to go, PF5 and BRF5. Let's see. So we have option D, PF5, and we have BRF5. So let's talk about PF5 first, where phosphorus is my central atom, and you have 1, 2, 3, 4, 5 electrons available for bonding, and all 5 of them are taken away by 1 fluorine atom, or rather, since we're talking about covalent bonding, let's say they're shared by fluorine atom. Okay, so here your steric number is equal to 5. This is going to be sp3d hybridization. You would expect a TBP geometry and you would see TBP shape. Great, so this is going to be a trigonal bipyramidal molecule. Now we have the last species to examine. We have BRF5. So here you have bromine as the central atom, and bromine has 1, 2, 3, 4, 5, 6 and 7 electrons available for bonding because bromine is a halogen. Okay, so now what happens here is that you have 5 fluorine atoms. So 1, 2, 3, 4 and 5, and then that leaves you with 1 lone pair. So you have 5 bond pairs and 1 lone pair. Steric number is going to be 5 plus 1, which is 6, which means sp3d2 hybridization. So in the case of sp3d2 hybridization, we would expect an octahedral geometry, but due to the presence of the lone pair, what we see instead is a square pyramidal shape. Okay, so this is square pyramidal, right? I'm going to mention that here. So this is TBP, this is square pyramid. Alright, great. So despite knowing that option B is the answer, we solved the entire thing, and it did not take a lot of time considering we had 8 molecules to solve. So option B is going to be the one where you have the pair having identical shapes, and option B is going to be the right answer to this question. So here they're saying the number of unpaired electrons in O2 molecule is going to be what? So here the theory that we are going to apply is the molecular orbital theory. And first of all, we need to calculate the number of electrons that we are talking about. So oxygen, the atomic number is 8. So 8 into 2, because you have 2 oxygen atoms. So 8 2s are 16. So we have 16 electron system, which means we are going to write the electronic configuration or the order of orbitals for more than a 14 electron system, right? So let's go ahead and write that. So you have sigma 1s less than sigma star 1s. Then you have sigma 2s is less than sigma star 2s. This is less than sigma 2pz. This is less than pi 2px, which is equal to pi 2py, which is less than pi star 2px. This is equal to pi star 2py. And then you have sigma star 2pz. Okay, so this is what you have. Now let's see, we have 16 electrons. We have 16 electrons to account for. So let's start filling them up in these orbitals. So you have 2, 4, 6, 8, 10, 12, 14, 15 and 16. Okay, so I mean, we've done chemical bonding quite a long time ago. So I hope you're comfortable with this, with me just filling up the electrons. And you can see that I have 1 unpaired electron here and 1 unpaired electron here. Because they are degenerate orbitals, I am not allowed to fill, 2 electrons in pi star 2px. That cannot happen because they are of the same energy, okay, which is why I'm required to fill 1 and 1. Done? So now, What can we see? We can see that we have 2 unpaired electrons, and that's here in option C. So option C2 is going to be the right answer to this question. Alright, so in this question, they're saying that 50 ml of a mixture of ammonia and dihydrogen was completely decomposed by sparking into nitrogen and hydrogen. Okay. 40 ml of oxygen was added and the mixture was sparked again. Fine. After cooling to the room temperature, the mixture was shaken with alkaline pyrogalol solution and a contraction of 6 ml was observed. Fine. Calculate the percentage by volume of ammonia present in the original mixture, and these are your options for the percentage of ammonia. Okay. So, see, first understand what is the premise of the question and what is the question trying to ask you. First thing is, you have a mixture of ammonia and dihydrogen. You have NH3 plus H2, right? And this entire mixture was sparked and allowed to decompose, which means what? Hydrogen is not going to decompose any further. Hydrogen is going to remain dihydrogen. So this ammonia, right? This was decomposed into N2 plus H2. We have not balanced it. This is just, what the reaction looks like qualitatively, not quantitatively. Fine. So you have this, then you have, the original hydrogen that was present. Now this mixture of N2 and H2, this was, so to this oxygen was added, right? So now you have N2 plus H2 plus O2, right? You have these three gases in the mixture. 40 ml of O2 is added here, right? And again, the mixture is sparked. Okay, so when you spark this mixture, what is going to happen? The reaction that happens is between these two. H2 plus O2 is going to give you H2O. Again, not balanced, just, the qualitative aspect of it. So this gives you H2O. What about N2? N2 will not react. N2 will not react with O2 because nitrogen has, a triple bond, right? The dinitrogen has a triple bond between it, which means it is a very strong bond to break. It's not going to break that easily, so you need a catalysis, you need certain temperatures. So N2 plus O2, that reaction mostly what we do is we ignore. Okay, unless you have very specific conditions which you will study later. Here you can say that this is not reacting. H2 plus O2 is the reaction that we'll be focusing on. Okay, now, but what you need to understand is all the O2 was not consumed. Some O2 was consumed to make water. Some amount of O2 was left. And how am I so sure that some amount of O2 was left? Because when you took that final reaction mixture or final product mixture, when you took that and when we allowed that to cool down to room temperature and we added alkaline pyrogalol to it, there was a reduction in volume that was observed. That reduction in volume was 6 ml. What does this have to do with the fact that oxygen is present? See, pyrogalol is used to absorb oxygen, right? This is what we've studied in idiometry, that pyrogalol is used to absorb oxygen, right? So here the contraction of 6 ml that was observed, this 6 ml has, basically been the volumetric reaction with oxygen. Okay. So this is what is happening here. So we know that some oxygen was definitely left. From here, they want us to find out what was the percentage of ammonia in the original mixture by volume. Understood? Now, one thing is nice that they are talking about it in terms of volume through and through, which means we can directly take a volume-volume ratio. Why? Because we know that volume-volume ratio is nothing but your moles-moles ratio. Okay, this you can simply think about it in terms of Avogadro's law. They've given us volumes directly. You can say that one volume of, whatever is the stoichiometric coefficients, based on that, instead of saying number of moles, we can directly say volumes. This much is fine. Okay, so that's very helpful. Let's get started. I hope the entire premise is clear. We'll be solving it completely. So, of course, I'm still here with you to solve it. Let's see. So, what do we have here? We have a mixture of ammonia and hydrogen. Okay, I'll say that initially ammonia was X and hydrogen was 50 minus X ml in the given mixture. So X ml of ammonia, 50 minus X ml of hydrogen. Initial composition of the mixture. Basically, if I find out this X, then I'll be able to find out the percentage of ammonia by volume in the mixture. Right? So the aim is to find out X. So, see, now what happened? Now what happened is that this ammonia has dissociated to give you N2 plus 3H2. Okay, this is what is happening. Cool. So if you have X ml of ammonia to begin with, okay, 1 second, sorry, we'll have to balance this, right? This will be 2. Yeah, now this is balanced. So if you have X ml of ammonia to begin with, after the reaction you will have X by 2 ml of nitrogen and 3X by 2 ml of dihydrogen. This is what you will have. So now when you talk about the current reaction mixture, once ammonia has decomposed after sparking, then your reaction mixture looks like this. So you have N2 plus 3H2 plus H2. Okay, so this N2 is X, 3H2 is this 3X by 2, and your H2 is 50 minus X. I have written it as 3H2 and H2 separately, just so you know that, you know, this is one thing and this is the other number, and we're going to add up those two things. So now add this entire thing. Your current reaction mixture looks like this. So you have X by 2 as your volume of dinitrogen plus, let's see, 50 plus X by 2, correct? Okay, plus 50 plus X by 2 as your volume of hydrogen. Okay, you have this. Now what do we have to do? Now you have 40 ml of oxygen reacting. So now the reaction you need to look at is H2 plus O2 gives you H2O. But we need to balance this. So this will be half. And now your reaction is balanced. Now what can I say? I can say that whatever, see, this is the volume of dihydrogen, right? So if I say volume of dihydrogen is Y, then the volume of O2 required will be Y by 2. Okay? And 40 minus Y by 2 has reacted and the rest of it is left unreacted, which is what was absorbed by the pyroglycol solution. I'll repeat it, listen carefully. So if I say that we know that 40 ml of oxygen was shaken into the reaction mixture, correct? So what does it mean? It means that out of 40 ml, this Y by 2 ml, this new variable that I'm assuming, this Y by 2 ml was used up in the reaction and 40 minus Y by 2 is left unreacted. 40 minus Y by 2 ml is left unreacted, and that unreacted oxygen was absorbed by the pyroglycol solution. Okay, so 40 minus Y by 2 is given to you, right? Okay, so 40 minus Y by 2 is given to you as 6 ml. 6 ml reduction in volume was given to you. So 6 ml is absorbed by the pyroglycol solution, which means what? Which means you have 80 minus Y is equal to 12, or 80 minus 12 is equal to Y, which means your Y is this is going to be 68 ml. Okay, which means what? Your volume of hydrogen, right? Volume of dihydrogen gas that was involved in the reaction, this is equal to 68 ml. And what do we know? We know that that value is 50 plus X by 2. Okay, so 50 plus X by 2 is equal to 68 ml. So what do you have? X by 2 is equal to 18. So which means X is going to be equal to 36 ml. And what was X? X was the volume of ammonia in the initial reaction mixture. Which means what? Which means when you calculate volume percentage of ammonia in the original mixture, you're going to get 36 divided by total volume, which is 50, multiplied by 100. Now this is nothing but 72%. And that is here in option D. So option D, 72% is going to be the right answer to this question. Okay, so here they're saying the degrees of freedom of oxygen gas molecule at normal temperature is going to be what? So what do we know about oxygen molecule? We know that oxygen exists as O2 in its gaseous state, which means it's a diatomic molecule. Okay, so for a diatomic molecule, you can talk about two kinds of degrees of freedom. Okay, it can be translational, okay, or it can be rotational, right? So from a translational point of view, you have 3 degrees, and from rotational point of view, you have 2 degrees of freedom. So when you add up both of them, 3 plus 2, 5. Okay, the total degrees of freedom of the oxygen gas is going to be 5, or in fact, for that matter, if you took any homodiatomic gas molecule, it would be 5, right? 5 is here in option B. So option B, 5 is going to be the right answer to this question. Okay, so here they're saying calculate Q, W and delta U. Okay, for the isothermal reversible expansion of 1 mole of an ideal gas from an initial pressure of 1 bar to a final pressure of 0.1 bar at a constant temperature of 273 Kelvin. Everything is given to you in the question. Substitute in the formula and find out the answer. Very simple. They're saying isothermal reversible expansion, which means first thing is delta U is equal to 0. So delta U is equal to Q plus W makes it Q is equal to minus W, right? So from here, let's see, what do we have? Option A I'm going to discard because it's saying W is equal to Q is equal to delta U is equal to 0. That's not true, okay? Option B is saying W is equal to Q, so I'm going to discard that as well because we got W is equal to minus Q, okay? Because of which now it's between options C and D. And you can see it's 5.22 kilojoules and 6.22 kilojoules, which means we do have a lot of room for approximation. So let's go ahead and, squeeze that opportunity. We have W is equal to minus 2.303 nRT log of P initial by P final, okay, in terms of the parameters that we have been given. So now we have minus 2.303, N is 1 because we have 1 mole, R is going to be 8.314 because we are talking about it in terms of kilojoules. So I will convert this to kilojoules later. Temperature 273 Kelvin, log of initial pressure is 1 bar, final pressure is 0.1 bar. Okay, so log of 10 is what we are getting. So minus 2.303 into 8.314, which I will write it as 25 by 3 because I want to approximate. Okay, into 273. So 273, I'm going to write it as approximately 300. Okay, I have a lot of margin for approximation, so I'm going to approximate it to 300 multiplied by log 10 is 1. Okay, so this will cancel out, you'll get 100. And then, okay, I guess we will have to calculate. So I'll write 25 as 100 by 4. So minus 2.303 by 4 into 10 to the power of 4 joules. This is what I have so far. I'm going to go ahead and cancel. So cancel this once. 2.3, right? So 2.3, the closest thing that you can do is write 2. So this is already 0.5. You have 30, so 30, so do 7. You have 28, so 2 is left. 23, so again we'll write 5. Okay, and 7, 5. Like you can write this. So now you have 0.57575 into 10 to the power of 4 joules. Convert this to kilojoules. So you will get 5.7 kilojoules. Correct? Okay, great. So, well, we got 5.7 kilojoules, but this is going to be a negative value, correct? Because this is work done. So, this is work done. So, which means here they're talking about minus W. So, minus W is going to be 5.7 kilojoules. And okay, so now the problem is this is between 5.22 and 6.22. So now what do? Now I want you to think how you've made the approximations, where you've increased the numerator, where you've decreased the denominator and all of that. And I can tell you that here what I have done is this is my biggest approximation, taking 273 as 300, which means I have increased the numerator. So the value that I get, okay, that value is greater than the answer, which means my answer that I am expecting is going to be less than 5.7. Okay, with that in mind, less than 5.7, you have only 5.22. So I can, discard, or I can eliminate option D, which means option C is going to be the right answer to this question.